One of the important applications of the normal distribution, and one of the primary motivators for why the normal distribution is so central in probability theory, is the so-called central limit theorem. It really is the central limit theorem in the sense that it's a fundamental property of summations and averages of random variables or samples of random variables. And I think you're all familiar with it, but let me just quickly review it. And this is only one statement. There are many versions of the central limit theorem. All have, in effect, the same consequence. They differ by making weaker and weaker assumptions about the random variable. So here we have a fairly specific application where we're going to assume that the xi is a collection of independent, identically distributed random variables. Notice we're not assuming they're normal. We're assuming they're independent and identically distributed. So, for example, they could be uniformly distributed on the interval 0, 1 as just a mental framework. They could be anything we want. We're going to assume that they, because they're identically distributed, that they all have the same mean, mu, and the same variance, sigma squared. So the central limit theorem has two versions. One, and they're identical, just using properties of expectations, but I like to state both so you can see the symmetry. One statement deals with the sum of the random variables, and there are many applications that use the sum, and the other statement uses the average. They're the same statement. From one you easily derive the other, but just to see what the conclusion looks like in these cases. So the first statement, where we deal with define yn as the sum of n independent, identically distributed random variables, and they can be any distribution at all that has a mean and a variance. The central limit theorem says if I take the random variable y and subtract n mu and divide by the standard square root of n sigma, that as n gets large, the distribution of this random variable looks more and more like the standard normal distribution. In practice, once n gets 30 or more, one sees normality in a very compelling way. And in many distributions, n can be as small as 10 or 15, and one starts seeing in the value of this distribution, you see normality appearing. But it's a limit theorem. It really says as n gets increasingly large, it approaches normality. But for practical applications, finite n, one sees normality and can use that. It's not a difficult calculation to show that what we're subtracting in the numerator is the mean of yn. You can easily verify that the mean of yn, it's just a calculation we saw earlier, is n mu. And what we're dividing this difference by is the standard deviation of yn. You can easily see that the variance of yn is in fact n sigma squared. So what we're doing is taking the random variable yn, subtracting its mean, dividing by its standard deviation, and that is going to be a standard normal in the limit. So we're now it's easy for you to verify the moment assumptions that for any n, this random variable yn minus n mu over sigma, this is in fact has a mean of 0. I'll call it mu prime, and a sigma prime of 1. Easy, by prime I mean it's the mean and the standard deviation of this ratio random variable. Easy calculation. So the 0, 1 over here is no surprise. This random variable always has a mean of 0, always has a standard deviation of 1 for any n. The statement that's important here is that the distribution of these scaled random variables become normal. This second statement is identical but deals with the average of the sum instead of just the sum. But everything I just said holds equally well. The fact that this ratio function has mean variance 0, 1 is a simple calculation. The fact that the mean of Wn is just mu, and that its variance is sigma squared over n, is again a straightforward expectation calculation. You should verify all those. So both statements are the same. Take a random variable, subtract its mean, divide by its standard deviation. That transformed random variable always has the moments indicated, 0 and 1. The important statement in both cases is that the distribution of those random variables becomes normal as n gets large.